calculate power loss in a wire, we use the formula power loss equals current squared times resistance times length. In this scenario, the current is 2.7 amps. The resistance of 10 American wire gauge (AUG) copper wire is approximately 0.5 ohms per foot. The length is 4,400 feet, representing the round-trip distance. Plugging these values into the formula, we get power loss equals 2.7 squared times 0.5 times 4,400, which equals 31.29 watts. To determine the percentage of power loss, we divide the power loss by the total power and multiply by 100. In this case, the percentage loss equals 31.29 divided by 1200 multiplied by 100, which equals 2.61%. A long wire run introduces impedance and reactive currents, which can reduce system efficiency. However, at relatively low current levels, such as 2.7 amps, these effects are generally negligible. The impedance of the wire creates a voltage drop along the line. For a 2200-foot run at 440 volts, the voltage drop is less than 5 volts, a small percentage of the overall voltage. Capacitive and inductive reactance can create reactive currents that flow in and out of the wire, reducing the real power transmitted. However, at the system's current levels and frequency, these reactive currents are minimal. Based on this analysis, using 10 American wire gauge wire for a 2200-foot run at 440 volts and 2.7 amps is appropriate. The power loss is minimal, and the impedance and reactive currents are negligible. If the system operates at a higher current or lower voltage, the power loss and impedance effects may become more significant, requiring larger wire sizes. It is always good practice to use slightly larger wire sizes than calculated to provide some margin of safety and account for any unforeseen factors. When dealing with electrical systems, several factors need consideration to ensure safe and efficient operation. These include conductor sizing, voltage drop, and applicable electrical codes. For conductor sizing, the National Electrical Code (NEC) provides guidelines to determine the appropriate wire gauge based on the current it will carry. It is essential to consult the appropriate NEC tables, such as Table 310.15b16, to ensure the selected wire can handle the expected amperage without overheating. Voltage drop is another critical factor in long wire runs. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to no more than 5% for feeders and branch circuits. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times K times I times D divided by Cm, where K is the constant for the conductor material, typically 12.9 ohms for copper, I is the current in amps, D is the one-way distance in feet, and Cm is the circular mils of the conductor. For example, let's consider a circuit with a 20 amp load, a one-way distance of 100 feet, and using 12 American wire gauge copper wire, which has a circular mil area of 6,530. Using the formula, voltage drop equals 2 times 12.9 times 20 times 100 divided by 6,530, which is approximately 7.9 volts. If the source voltage is 120 volts, the voltage at the load would be 120 minus 7.9, which equals 112.1 volts. This represents a voltage drop of about 6.6%, exceeding the recommended limit. In such cases, you would need to increase the wire size to reduce the voltage drop. The NEC also provides guidelines for directing conductors when multiple wires are bundled together or run in conduit. This is necessary because heat can build up, reducing the ampacity of the conductors. Refer to NEC Table 310.15b3 for directing factors based on the number of current-carrying conductors in a raceway or cable. Always follow the NEC guidelines and local electrical codes to ensure the electrical system is safe, compliant, and operates efficiently. Consider a scenario where you have a 240-volt circuit powering a motor that draws 30 amps. The distance from the panel to the motor is 150 feet. To determine the appropriate wire size, you must consider both ampacity and voltage drop. First, refer to NEC Table 310.15b16 to find the ampacity of different wire sizes. For a 30 amp load, you might initially consider 10 American wire gauge copper wire, which has an ampacity of 30 amps at 60 degrees Celsius. However, to account for voltage drop, you need to perform a voltage drop calculation. Using the voltage drop formula, voltage drop equals 2 times K times I times D divided by Cm, where K is 12.9 ohms for copper, I is 30 amps, D is 150 feet, and Cm for 10 American wire gauge wire is 10,380 circular mils. Plugging in the values, voltage drop equals 2 times 12.9 times 30 times 150 divided by 10,380, which equals approximately 11.17 volts. The percentage voltage drop is calculated as voltage drop divided by source voltage times 100, which equals 11.17 divided by 240 times 100, resulting in 4.65%. This is within the recommended limit of 5%. However, if you anticipate the motor running continuously for 3 hours or more, the NEC requires you to increase the conductor size by 125%. In this case, 30 amps times 1.25 equals 37.5 amps. Now, you would need to select a wire size that can handle at least 37.5 amps. Based on NEC Table 310.15b16, you would need to use 8 American wire gauge copper wire, which has an ampacity of 40 amps at 60 degrees Celsius. Therefore, considering both ampacity and voltage drop, you should use 8 American wire gauge copper wire for this application. Always consult the latest edition of the NEC and local codes to ensure compliance and safety. When working with electrical systems, understanding the concepts of impedance, reactance, and power factor is crucial for efficient and safe operation. Impedance, denoted as C, is the total opposition to current flow in an AC circuit. It includes both resistance, R, and reactance, X. Reactance is further divided into inductive reactance, XL, and capacitive reactance, XC. Inductive reactance occurs in circuits with inductors or coils and is given by XL equals 2 times pi times F times L, where F is the frequency in Hertz and L is the inductance in Henrys. Capacitive reactance occurs in circuits with capacitors and is given by XC equals 1 divided by 2 times pi times F times C, where C is the capacitance in farads. The impedance, Z, is calculated as the square root of R squared plus XL minus XC squared. In a purely resistive circuit, the impedance is equal to the resistance. In a purely inductive or capacitive circuit, the impedance is equal to the reactance. The power factor, PF, is the ratio of real power, P, to apparent power, S, and is given by PF equals P divided by S. Real power is the power actually consumed by the load and is measured in watts. Apparent power is the product of the voltage and current and is measured in volt-amps. The power factor is also equal to the cosine of the phase angle, theta, between the voltage and current. A power factor of 1 indicates that the voltage and current are in phase and all the power is being used effectively. A power factor less than 1 indicates that the voltage and current are out of phase and some of the power is being wasted. Inductive loads, such as motors and transformers, typically have a lagging power factor, meaning the current lags behind the voltage. Capacitive loads have a leading power factor, meaning the current leads the voltage. To improve the power factor correction capacitors can be added to the circuit to counteract the effects of inductive loads. By improving the power factor, you can reduce the current drawn from the source, reduce losses in the system, and improve the overall efficiency of the electrical system. For example, consider a motor that draws 10 amps at 240 volts with a power factor of 0.8 lagging. The apparent power is S equals voltage times current, which equals 240 times 10, or 2400 volt-amps. The real power is P equals S times power factor, which equals 2400 times 0.8, or 1920 watts. To improve the power factor to 0.95, you would need to add power factor correction capacitors to the circuit. The size of the capacitor required can be calculated using various formulas and tools available online or through electrical engineering software. Understanding and managing impedance, reactance, and power factor is essential for designing and maintaining efficient and reliable electrical systems. When dealing with long wire runs in electrical systems, several additional factors should be considered to ensure optimal performance and safety. Firstly, consider the effects of skin effect, which becomes more pronounced at higher frequencies. Skin effect causes the current to flow primarily along the surface of the conductor, effectively reducing the cross-sectional area available for current flow. This increases the AC resistance of the conductor compared to its DC resistance. For long AC runs, especially at higher frequencies, this effect should be taken into account by using larger conductors or specialized cables designed to minimize skin effect. Secondly, consider the effects of electromagnetic interference, ME, and radio frequency interference, RFI. Long wire runs can act as antennas, picking up unwanted noise and interference from nearby sources. Shielded cables or conduit can help mitigate these effects by providing a barrier against electromagnetic radiation. Additionally, proper grounding and bonding techniques are essential to minimize noise and ensure a stable reference point for the electrical system. Thirdly, consider the mechanical support and protection of the wires. Long wire runs should be adequately supported to prevent sagging or excessive strain on the conductors. Use appropriate cable trays, conduits, or other support structures to maintain proper spacing and prevent damage. Additionally, protect the wires from physical damage such as abrasion, impact, or exposure to harsh environmental conditions. Fourthly, consider the ambient temperature and its effect on conductor ampacity. The ampacity of a conductor is based on a specific ambient temperature, typically 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher, the conductor ampacity must be derated to prevent overheating. Refer to NEC Table 310.15b16 and the associated correction factors to determine the appropriate derating factor based on the ambient temperature. Fifthly, consider the use of appropriate connectors and terminations. Use connectors and terminations that are specifically designed for the type and size of conductor being used. Ensure that the connections are properly tightened and torqued to prevent loose connections, which can cause overheating and arcing. Additionally, use antioxidant compounds on aluminum conductors to prevent oxidation, which can increase resistance and reduce the reliability of the connection. Finally, consider the coordination of overcurrent protection devices. Ensure that the circuit breakers or fuses are properly sized and coordinated to protect the conductors and equipment from overloads and short circuits. Perform a short circuit study to determine the available fault current at various points in the system and select overcurrent protection devices with adequate interrupting ratings. By considering these additional factors, you can design and install long wire runs that are safe, reliable, and perform optimally. Remember to always consult the latest edition of the NEC and local codes and to engage qualified electrical professionals for complex or critical applications. Let's delve a little deeper into calculating voltage drop and alternating current AC circuits, particularly when dealing with long wire runs. While the basic voltage drop formula, voltage drop equals 2 times K times I times D divided by Cm, provides a good estimate, it doesn't account for the effects of reactance, which can become significant in long AC circuits. A more accurate formula for calculating voltage drop in AC circuits is voltage drop equals the square root of VR squared plus Vx squared, where VR is the resistive voltage drop and Vx is the reactive voltage drop. The resistive voltage drop, VR, is calculated as VR equals I times R, where I is the current and R is the resistance of the conductor. The reactive voltage drop, Vx, is calculated as Vx equals I times X, where X is the reactance of the conductor. The reactance, X, includes both inductive reactance, XL, and capacitive reactance, XC. In most practical applications, the inductive reactance is the dominant factor, and the capacitive reactance can be ignored. The inductive reactance, XL, is calculated as XL equals 2 times pi times F times L, where F is the frequency in Hertz and L is the inductance of the conductor. The inductance of the conductor depends on the wire size, spacing, and geometry. Tables and calculators are available to determine the inductance of various conductor configurations. Once you have calculated VR and Vx, you can plug them into the voltage drop formula to determine the total voltage drop. For example, consider a 240 volt AC circuit with a 20 amp load, a one-way distance of 200 feet, and using 8 American wire gauge copper wire. The resistance of 8 American wire gauge copper wire is approximately 0.778 ohms per foot, so the total resistance is R equals 0.778 times 200 times 2, which equals 0.3112 ohms, considering the round trip. The inductive reactance of 8 American wire gauge copper wire at 60 Hz is approximately 0.187 ohms per foot, so the total reactance is X equals 0.187 times 200 times 2, which equals 0.748 ohms. The resistive voltage drop is VR equals 20 times 0.3112, which equals 6.224 volts. The reactive voltage drop is Vx equals 20 times 0.748, which equals 1.496 volts. The total voltage drop is voltage drop equals the square root of 6.224 squared plus 1.496 squared, which equals approximately 6.4 volts. The percentage voltage drop is calculated as voltage drop divided by source voltage times 100, which equals 6.4 divided by 240 times 100, resulting in 2.67%. This is within the recommended limit of 5%. By using the more accurate voltage drop formula that accounts for reactance, you can ensure that your calculations are more precise, especially in non-AC circuits. Always consult the latest edition of the NEC and local codes and to engage qualified electrical professionals for complex or critical applications. Let's talk about the importance of grounding and bonding in electrical systems, especially in the context of long wire runs and microhydro projects. Grounding and bonding are critical for safety and to ensure the proper operation of electrical equipment. Grounding refers to connecting the non-current carrying metal parts of an electrical system to the earth. This provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to trip and clear the fault. Bonding refers to connecting together all the non-current carrying metal parts of an electrical system to create an electrically continuous path. This ensures that all metal parts are at the same potential, minimizing the risk of electric shock. In a microhydro project, grounding and bonding are particularly important due to the potential for exposure to water and other environmental factors. The grounding system should be designed to provide a reliable path for fault current to flow, even in wet or corrosive conditions. The grounding electrode system should consist of one or more grounding electrodes, such as ground rods, ground plates, or underground metallic water pipes. The grounding electrodes should be installed in accordance with NEC requirements and should be properly sized and connected to the grounding electrode conductor. The grounding electrode conductor should be connected to the main grounding busbar in the electrical panel. The main grounding busbar should be bonded to the metal enclosure of the panel and to any other metal parts of the electrical system. Equipment grounding conductors should be run with the circuit conductors to all electrical equipment such as motors, generators, and appliances. The equipment grounding conductors should be connected to the equipment grounding terminals on the equipment and to the grounding busbar in the panel. In long wire runs, it is particularly important to ensure that the equipment grounding conductors are adequately sized to provide a low impedance path for fault current. The size of the equipment grounding conductor should be based on the size of the circuit conductors as specified in the NEC. Additionally, it may be necessary to install supplemental grounding electrodes along the wire run to improve the effectiveness of the grounding system. Bonding should be performed on all metal parts of the electrical system, including metal conduits, metal enclosures, metal frames, and metal supports. Bonding jumpers should be used to connect together all the metal parts to create an electrically continuous path. The bonding jumper should be sized in accordance with NEC requirements and should be properly installed and tightened. In wet or corrosive environments, it is important to use corrosion-resistant materials for grounding and bonding connections. Stainless steel or copper connectors and conductors are often used in these applications. Additionally, it is important to protect the grounding and bonding connections from physical damage and corrosion. The connections should be installed in a protected location and should be coated with a corrosion-inhibiting compound. By properly grounding and bonding the electrical system, you can significantly reduce the risk of electric shock and ensure the safe and reliable operation of the Microhydro project. Always consult the latest edition of the NEC and local codes and to engage qualified electrical professionals for complex or critical applications.